Okay, I had to move my setup because my battery died. Alright, so when we take the antiderivative of 1 over x, we get the natural log of x. So the antiderivative of this will be the natural log of VC. It's very hard to write through my phone screen. And this is going to be evaluated over VS and VC. So from VS to VC. Okay? And that's going to equal the antiderivative. And by the way, we get this from a table. There's a table of antiderivatives for different equations. You don't have to. You can actually do the math on this, which is just another set of summations that will give you the antiderivative, but the table is the fastest way rather than reproving it every time. And so negative 1 over RC becomes negative T over RC. Nope, and then we're evaluating this from 0 to T. So that becomes T because this is a constant at this point. R times C, 1 over R times C is a constant. And so the antiderivative is just the variable that you're working with times this constant. So negative 1 times T, okay? And so now we're very close. We just have to evaluate this. So the natural log of VC or VS minus the natural log of VC. So it's this one minus this one. Oh, no, I'm sorry. I got that backwards. It's this one minus this one. So, the natural log, ln, wow, murdered it through the phone there. A little laggy. Natural log of VC minus the natural log of VS. Is equal to, now we plug T into here, so we get negative T over RC minus, then we plug 0 into here, 0 over RC. And 0 over anything is 0. And anything minus 0 is just that, anything. So this whole entire term cancels out. And then there's some natural log rules going on here. We can combine 2 logs into 1 log. And so this becomes the natural log of VC over VS. And that is equal to negative T over RC. Okay? So, how do you get rid of a natural log? We have to solve for VC. That's the equation that we're trying to create. So you can get rid of the natural log with the exponential function. So e to the natural log of VC over VS is equal to e to the negative T over RC. Okay? E to the natural log cancels. And you're left with VC over VS. So we're going to move this up here. We're going to say VC over VS is equal to E to the negative T over RC. And now we're solving for VC, so we have to multiply this VS over. And what we end up with is the voltage of a capacitor with respect to time, which I didn't write down, is equal to VS times E to the negative T over RC. Now, does this equation look familiar to any of you? This is the discharging equation for a capacitor that you all know and love. We have created this equation ourselves. It was not given to us right now. We did not know this equation. We started with this. We started with a relationship, some conversions of relationships, more conversions of relationships, making these numbers more normalized, summing them from points to points, more conversions of relationships, and more conversions of relationships, until finally we end with this equation, which is written in every math book or every circuits or electrical engineering book, radio theory, everywhere this thing's written. So there you go. There you have it. That is the magic of calculus. So I've got some spiral calculus to show you, but I don't want to upload it until I get the math right. There are some things inside of this particular example I showed you which had some math in it that I think you should see before we do the spiral equations, because there's a lot of vector closed loop integrals within integrals within integrals. There's a multi-variable calculus going on. And so there you have it. Peace.